Hi guys, my name's Jamin, and today we're going to be talking about projectile motion. We're going to be deriving some key results, and we're going to be applying it to an exam-style question. So, in projectile motion, you guys will be working with equations in two dimensions. We call this the parametric form of a projectile's motion. So basically what it does is it allows us to express the motion of a projectile as a position in terms of a time in both the horizontal and vertical directions. So what these equations mean is that at any point, you can get an x position based on t, a time value, and the same for y, and all you need is the time value itself, as well as an initial velocity and an initial launch angle. That is the v and the theta. So you need to be able to derive these equations fairly quickly, and I'm going to do that on the next slide for you. And you also need to be able to combine them to form the Cartesian equation for a projectile. So this is the equation that would appear on, say, a number plane if you plotted it. It links x to y directly rather than linking x and y to time separately. You need to be very used to both of these, being able to derive both very quickly, especially this Cartesian equation at the end. This is a really important result. It comes up in a lot of exam-style questions. So let's look at how to derive these. So before we get into the actual derivations, we need to understand what this angle theta and what this v actually are, and how they relate to a horizontal and a vertical sort of component of motion. So when we launch our projectile, this is what's happening. We're launching our projectile at a velocity v, at an angle theta to the horizontal. Now when we do that, this is an idea that if you do HSC physics, this will be quite natural to you. Instead of expressing it as a single velocity in a diagonal direction, we can instead express it as a horizontal velocity, Vx, which I've got in blue, and a vertical velocity, Vy. And what this does is it forms a right-angled triangle. And what this lets us do is express Vx and Vy in terms of our actual launch velocity V and the launch angle theta. The way this works is pretty simple. If we take the sine ratio of this triangle, or of this angle theta, we get Vy on V. And what that implies is that Vy is equal to V sine theta. And in a very similar way, if we take the cos ratio, we'll get Vx on V, and that implies that Vx is equal to V cos theta. So these represent the initial velocities, right? So these are, when we launch the projectile, the velocities that it has in the horizontal and vertical directions. With this in mind, we can now derive the results as we need them. So I'll just leave that on the side there. Now, to start by deriving the results, let's start in the x direction. We know that in the x direction, acceleration will be equal to 0. There's no horizontal forces at play. There's no air resistance, there's no friction, so there's no horizontal acceleration. If we integrate that, we get an unknown constant. But we know that this constant has to allow for the initial horizontal velocity to be equal to what we just found. So what that means is that when t is equal to 0, x dot should be equal to v cos theta. And since there's no t in this equation at all, that just means that C1 has to be v cos theta. So x dot is equal to v cos theta. Now to go to a position equation, we integrate again. The important thing to keep in mind is that this equation here, this v cos theta, that is not a variable, right? It's just two constants, v, which is a constant, and cos of the angle theta, which is also a constant. So we're not integrating a variable here. We're integrating a constant value, which means all we do is add, let's keep it in black, is add a t value. Right, so we just add the t on. We still have another constant, but assuming we start from the origin, that means that when t equals 0, x is equal to 0, and that implies really easily that that constant is also 0. So the final equation for position in the x direction is just vt cos theta, as we'd expect. It works very similar in the y direction. I'll move a little bit faster this time. In the y direction, we do have an acceleration. It's a negative g, where that is just gravity, right? So usually they'll define that for you as 10 meters per second if they define it at all, but it's just g in general. Integrate that, we're integrating a constant, so we get negative gt plus a constant. Now, we know that when t is equal to 0, our vertical velocity needs to be equal to v sine theta. That's what we proved with that right-angled triangle over on the left there. What this implies is that c3 has to be equal to that v sine theta. That's because if we apply t equals 0, this first term here will vanish, so it has to come from here. So that means that our vertical velocity is v sine theta minus gt. If we now integrate that, very similar to the left, this first term will evaluate to vt sine theta, and this second term will go to 1/2 gt squared. And we'll have another constant at the end, but again, by the same logic as on the left, since t is 0 and y is 0, assuming we're starting from the origin, c4 will also be 0. So our final equation is that the y position is vt sine theta minus 1/2 gt squared. So that's a derivation of those two really crucial results. The other thing you need to be able to do is to link these into a Cartesian equation. The way we do that is fairly easy. All we do is start from our x equation, and we're going to rearrange to put t by itself. And that gives us t is equal to x on v cos theta. Now that we have an equation for t, we can replace the t in the y equation with our new expression. So what that means is that we'll have v times x on v cos theta times sine theta. That's our first term. And then at the back, we'll have g on 2 times x on v cos theta all squared. We can tidy this up a little bit. In the first term, the v's cancel, and sine on cos, that's tan. So this first term actually simplifies to just x tan theta. At the back, we have an x squared and a v squared here and here. Neither of those will cancel, so we'll pull them out the front with the g on 2, and we'll write gx squared on 2v squared. Then what we're left with is a 1 on cos theta squared. Now 1 on cos is sec, so that is sec squared theta. So that's the Cartesian equation of our line. The y-coordinate at any given time is given by the x-coordinate into this equation in terms of v and theta. Another common thing that you will want to know how to do is this sec squared theta can be converted to 1 plus tan squared theta. What that means is that you can write y is equal to x tan theta minus gx squared on 2v squared of 1 plus tan squared theta. And I'm not going to do the rest of the working, but what this essentially is a quadratic equation in terms of both x and theta, or tan theta specifically. This is something you'll do a fair bit depending on the application, so make sure you are aware of this conversion here, this sec squared to 1 plus tan squared. That's a really important thing to know, or at least have seen, to have in your toolkit. Right, so with all that theory out of the way, let's get into a HSC question. This is from my HSC exam. So, we're told that the takeoff point O on a ski jump is located at the top of a downslope, so that's sort of the origin here. The angle between the downslope and the horizontal is pi on 4, that's labelled in the diagram. And we're told that a skier takes off from O with velocity v meters per second at an angle theta to the horizontal, exactly what we've just been talking about. And we're given the restriction that theta has to be less than pi on 4, or 45 degrees. The skier then jumps up and lands on the downslope at some point P, and that has a distance d meters from O. What we're asked to do with this is not to prove the results. In this case, they've given us the results we're allowed to use. And it's really important that you don't waste time proving it if they've given it to you. But if they don't give it to you, you must prove it. So make sure you're aware of that difference. The first step is just to show that the Cartesian equation of the path of the skier is given by y equals x tan theta minus gx squared on 2v squared of sec squared theta. We have actually already done that, so I'm not going to do it again. Consider that done. That's just done using the proof I showed you earlier. The next step, though, is more interesting. We're asked to show that d is equal to 2 root 2 v squared on g times this product of a few trig functions here. This is a 3-marker, it's fairly serious. Then we're heading into some calculus work because we're asked to find a derivative and we're asked to find a maximum value. So this is a good question. It ties in projectile motion to a fairly difficult maximum minimum problem as well, which is why I've picked it. So let's get into it. So skipping straight ahead to the second part, to find this d expression. When we're asked to do something like this, or anything in projectile motion, you always want to go from your previous results. Very rarely will they ask you to do something that doesn't play into a later result. So I've started with the Cartesian formula we found in part 1. What we're asked to find is d. Now they've sort of given you a clue on this because they've put this sort of plot here in the left on a number plane. D is just the distance from the origin to this point here, this point P. So logically, the first good step would be to find the coordinates of P. So the question is, how do we do that? Well, we have an equation for this curved parabolic line here. This line, this parabola here, is given by this equation. What we essentially want is the intersection of that parabola with the downward sloping line. So normally you do that with simultaneous equations. Problem, of course, is we don't have an equation for that line yet, but we can easily get one. All we do is consider, well, it's a line through the origin, and it has a gradient corresponding to an angle of negative pi on 4. Remember, if we measure an angle from the x-axis, that's a negative angle there. So the gradient is actually the tan ratio of negative pi on 4, which is just negative 1. This line has a really easy equation. It's just y equals negative x. And look, if they'd given you that equation in the question, this part of the problem would be a lot easier. But they haven't. You have to be switched on enough to notice that. And in my HSC exam, it probably took me a few minutes to think of doing it in this way. But this is the approach. It's always about working backwards. I need a distance. Therefore, I need a point. Therefore, I need an equation. Therefore, I need a gradient. And you work backwards until you find something that you actually have, and then you go back forward. That's almost always the best approach. So, what we're doing is we're finding where both of these equations are true. This y equals negative x, and our equation of motion up here. So, we just put them equal to each other. Negative x equals x tan theta minus gx squared on 2v squared sec squared theta. So our objective here is to get the x by itself, and that's actually not too hard here. To make it a lot easier, what we can do is cancel one x off. The reason we're allowed to do that is because we want the point P. P is clearly not at the origin, which means we don't care if we lose x equals 0 as a solution. That's the origin intersection. We want the other. So we're allowed to safely do that. And we should acknowledge why. We should say we've cancelled an x, and we've done that because x is greater than 0 at point P. That makes the rearranging infinitely easier because we just have -1 equals tan theta minus gx on 2v squared sec squared theta. And from that, all we do is do a bit of rearranging. So we'll get gx on 2v squared sec squared theta is equal to 1 plus tan theta. Then we'll just move everything to the other side. So we'll get 2v squared on g times 1 plus tan theta over sec squared theta. And from there, just make sure you've understood all the preceding algebra. We'll go on to the next slide to make it look a bit more like the result they want. So there's the result we've just proved. Now to keep working on it, what we notice in the result is that they've got a sum of terms that's not on a fraction. So logically that means that we should combine the terms on the top and bottom of this in some way. That's not too hard. So if we just write out that term at the front, 1 on sec squared is just cos squared. And tan on sec squared, well, let's think about that a bit more carefully. If you've got tan divided by sec, you've got sine on cos divided by 1 on cos, and in this case there's a squared. Remember, that's the same as saying sine on cos times cos squared. So what happens is, however you think of it, one set of coses cancels, and so that second term just ends up being sine theta cos theta. So this is the x-coordinate of the point P, right? Now, we don't actually have to find the y-coordinate to find the distance if we're clever, because what we notice is that, recall this line has an equation of y equals -x. What that means is that the y-coordinate will immediately be just the negative of this x-coordinate. So what that means is that in the distance formula, when we're calculating d, which is just the square root of the x-coordinate squared plus the y-coordinate squared, because we're taking it from the origin, we can just replace that with the square root of 2x squared, which is root 2x. Remember, distance is a positive quantity, so we don't care about the negative square root. So x is just distance on root 2, which means that the distance is root 2 times x. You can do this in a slightly longer way. You could even find the y-coordinate directly, although I think that'd be a fairly complicated bit of algebra. You'd end up with just the negative of this anyway. But this, I think, is the simplest approach. So the distance is just root 2 times that result there. And that is what gives us what we need. And all they do is factor out a cos theta. That's the result we need to prove. In terms of how marks would be structured for that proof, you'd get a mark for the finishing touches. You'd get a mark for any kind of indication that you've noticed the equation of the line or in some way attempted to find a point of intersection, and then probably a mark for getting to this stage as well. This next question is really just a differentiation. So as much as it might be algebraically intensive, it's actually not conceptually difficult to perform. Even if you didn't understand how to do any of the actual projectile motion stuff from earlier, now we're just into calculus. So when we differentiate this, keep in mind that this number at the front, this 2 root 2 v squared on g, that's just a constant. So that's just going to stay out the front of whatever result we get. Don't bother trying to include it. Just immediately write it, and we'll put the rest of the result in a big set of square brackets. So we have a derivative of cos times cos plus sine. This is a product rule question. You could do this by expanding and then using the chain rule, but I'm just going to do the product rule because that's the form it's in. So, product rule says we use the first function times the derivative of the second function, which derivative of this is negative sine plus cos. Then we add the second function times the derivative of the first function. So let's see if we can tidy that up. We get 2 root 2 v squared on g out the front unaffected. Then let's just expand. We have negative cos sine plus cos squared theta minus cos theta sine theta again minus sine squared theta. And so we get to here, and at this point it's important to keep an eye on the result. What are we actually heading towards? We need a cos 2 theta to appear, and we need a sine 2 theta to appear. You should be able to see both of them in there already. You notice we have a cos squared theta and a minus sine squared theta. That is the double angle expansion of cos. That's cos 2 theta. So those two bits that I've circled in blue will turn into cos 2 theta. As for the sine 2 theta, well, we have minus sine cos minus sine cos. That is minus 2 sine cos. That is the double angle expansion for sine. So those green bits will turn into minus 2 sine theta, or sine 2 theta rather. And so that's the proof. It's just about noticing the double angle results inside the result of your differentiation. To show that d has a maximum value and then to find it, all we need to do is put this derivative equal to 0. So let's start by doing that. Again, this constant out the front, this 2 root 2 v squared on g, it's kind of annoying that it's been there this whole time because it doesn't play into this at all. It's guaranteed to be a positive number, so we don't really care about it. The only thing that can be equal to 0 is in the brackets. So, the derivative being equal to 0 just implies that cos 2 theta minus sine 2 theta is equal to 0. And that's a fairly easy trig equation to solve, right? So if you put one of these on the other side and then divide, you get an equation in terms of tan. So it's pretty clear from looking at this, also keeping in mind that theta has to be an acute angle, that 2 theta has to be equal to pi on 4. So theta is pi on 8. So you'd get a mark just for getting to here. The next step is to prove that it is actually a maximum value. Now this one's right on the fence of whether you want to do a second derivative test. You'd have to differentiate this expression up here, or whether you want to just do a point either side check. I'll leave that to you guys to do. But what you'll find is that indeed, that d is maximum when theta is pi on 8. Remember to do the proof. In your version, in your exam working, you must do a proof in this gap. So this is probably one of the harder projectile questions that's been asked in the last few years. It's a good question. It combines ideas of projectile motion with more basic, or at least less conceptually difficult ideas of maximization and optimization. This is an accessible question. Even if you can't get that middle bit to prove the result, you can do the differentiation and you can do this maximum value question. Half of the marks are very accessible to you. As a few last minute tips for projectile motion, these are probably questions you want to leave until last, right? You want to make sure you've got the easy marks first before you start tackling the hard stuff. So if you're sitting on a projectile motion question, you can't quite crack it, move on, get some other marks first, and then come back to this at the end of the paper when you're trying to sweep the rest of the marks into your bucket. You want to know the basic patterns these questions can take, and I'll show you them on the next slide. But beyond that, be very careful with your algebra. The amount of people I see make mistakes like negative, like forgetting a sign or forgetting a power, really easy to do with all these variables flying around. So be really careful and ensure that you consider which terms are constants and which are not. So in the question we just did, a lot of students would forget that v and g are not variables. They might try and differentiate that term at the start, or even perhaps do a three-way product rule. Always keep in mind what can change and what can't, what you're differentiating with respect to, all of that sort of stuff. And really importantly, if you're not given the equations, you must derive them. Of course, you've now got a formula sheet, so it's possible you might not get asked this anymore, but you should be prepared to do it if they ask you. To give you an idea of just how predictable these questions can be, here's a picture of what they've done the last 5 years. So today we did HSC 2014, and you'll notice that it starts with a very typical lead-in, finding the Cartesian equation, and then we go to more complicated stuff. This is the same pattern that they use and have used for the last 5 years. It's always a typical lead-in scenario, followed by something that maybe hasn't been asked before, or at least isn't very stock standard. Last year's HSC, they got lucky. Everything was stock standard. This year's question is likely to be a bit tougher, but it's almost definitely going to start with something standard: a Cartesian equation, a range, a time of flight, a max height. Go back through your HSC papers, make sure you can do, at the minimum, these first steps. That way you're guaranteed to get at least a few marks, and the harder stuff you can work on later. But those first few things, the ones in red, are things you must be able to do, and they must be completely instinctual. If you want to see steps on how to approach those red ones, or even the more complicated things that appear towards the end of the problems, you can always come and ask me on the ATAR Notes Extension 1 Math forums. We have a place for you to ask questions, even things like scaling and stuff, we can talk about that too. If you have any questions at all, we'll be happy to lend a hand. So be sure to jump on there. There'll be a link after the video to get to that forum.